All right, thank you very much. My name is Svenne Freund. I was PhD student at the Institute of Engineering Thermodynamics at the Hamburg University of Technology until 2021. At this time, Gerhard Schmitz was the head of the institute, and today Arne Sperfock, who's also here, is head of the institute. And I'm going to present the results of the implementation of model predictive control in a large administrative building. If you had a very close look to the slides of Arash at the beginning, we were into the 1.9% of the field test demonstration of MPC actually, and this is what I want to present here. First of all, if you click on this, I guess. Yeah. Some very short introduction and motivation. I think there's no real need to emphasize the importance of energy efficiency in buildings. Building operation worldwide accounts for 30% of the final energy consumption and 26% of the energy-related greenhouse gas emissions. So reducing the energy demand of buildings is a very effective climate protection measure. On the other side, we've got user comfort inside buildings, which is also a very important aspect, as we spend 90% of our lifetimes inside buildings. And in some climate region, even the heating or cooling of buildings is essential for survival. So comfort inside building has a significant impact on our health and performance. These two factors here are often like contradicting each other. They are kind of opponents. So the most energy efficient building is the one that's neither cooled nor heated nor ventilated, but it's not the most comfortable building, I guess. So what do we have on options to improve these two factors here in existing buildings? Of course, there's the classical energy efficiency refurbishment, like improving thermal insulation, improving the energy system in the building. And on the other side, there's the way to optimize the way a building is operated through hard and software measures. And that's where MPC comes into place, which is an advanced control technique that has proven in many simulation studies, but also in a few field studies, to improve the energy efficiency of buildings. At the same time, it can improve the user comfort inside buildings. So as you are all familiar with the concept of MPC, I won't go into the details here. I just want to use this scheme here to present the components that we've got here. And I would like to start with the demonstration building. The demonstration building that you can see here on the right-hand side is located in northern Germany. It's an administrative building, and it was built in 2013. It has a gross floor space of around 46,500 square meters. And as you can see here, it's split into 8 different building sections from A to H, with 7 low-rise building sections and 1 high-rise building section here. The building was planned and built as a very energy efficient and sustainable office building with an annual primary energy demand of around 60 kilowatt hours per square meter and year, and an annual heating demand of around 30 kilowatt hours per square meter and year. And it was investigated in a scientific monitoring project from 2014 to 2017, where we gathered a lot of measurement data during the first years of the operational phase of this building. And in the course of this monitoring project, 32 so-called reference zones or reference offices in the building sections A, C, E, and G were implemented. So these are just basically offices which are equipped with sensors for room air temperature, humidity, but also for occupancy and window handling in these offices. The building is primarily heated and cooled via concrete core activation of the ceiling. We could also call this a thermoactive ceiling here. And these thermoactive ceiling is by default controlled by just a simple linear heating curve. So the supply temperature of this heating circuit is linearly based on the outdoor temperature, and for the circulation pump we have just a simple time schedule. So all in all, this is just a simple rule-based controller here. Each of these building sections I've showed before, we've got 2 different thermoactive sealing heating circuits. So in total, we have 16 different heating circuits here in this building for these thermoactive sealing. And the MPC controller now just replaces this default control, and it's configured as a high-level controller, as you can see here. So it just calculates the optimized supply temperature here and an optimized pump operation here. Next, I would like to just shortly discuss the models that we used here in our MPC controller that we used. MPC highly relies on dynamic models presenting the thermal behavior of our building, and the accuracy of these models is actually crucial for the overall performance of the MPC controller. So these models should be quite accurate, but they should also be efficient in times of simulation, because we are using this in a nearly real-time optimization and control problem. And ideally, these models are transferable to other buildings, to other use cases. And we decided to just use simple gray box models here for the reference zones, these reference offices that we have in these buildings. And these are just a simplified physical model structure combined with parameter estimation using the monitoring data we gathered in the monitoring project. And here you can see the simple model structure. It's just a resistance capacitance model consisting of 7 thermal resistances and 4 thermal capacitance. So this is what we call this an R7 C4 model here. After we developed the models that the controller used, I would go into the details of the cost function optimization problem. The goal and objective of the MPC controller is obviously to minimize the energy consumption and maximizing the comfort in the building. Therefore, we've got 3 components in the cost function: the discomfort cost, which is the integral of the deviation between the room air temperature and some upper and lower limits for the temperature over the entire prediction horizon. The energy cost, which is just the amount of energy here that we used to heat the offices. And last, the cost for control input change, which is just which prevents the controller to have frequent, very fast changes on our optimization variable here. So the overall control optimization problem reads as follows. The optimized control variable U here results from the minimization of the weighted sum of these 3 components for the discomfort for the cost function with respect to some upper and lower limits for our control variable here. So next I would like to go into the details of the experimental results. First of all, the experimental setting. The period we investigated was from November 2020 to April 2021. And the MPC controller controls the thermoactive heating circuits here in the building sections A, C, and G. And all the other building sections, they remain at the default control strategy, the rule-based control strategy here. So this configuration here allows a detailed comparison of the MPC and the RBC strategy. in similar building sections under identical operation conditions here. The achieved savings that I will show you on the next slide are calculated against an expected heating energy demand. And this expected heating energy demand is the demand we expect for an MPC-controlled building section in this period here, but under RBC control. And to calculate this expected demand, we used the average heating demand of the past 6 years and did some long-term correction of this. So the results regarding the heating energy are shown here in this table. You can see the monthly absolute and relative change in heating energy with respect to the expected heating energy demand for the 3 MPC-controlled building sections. And as we can see, the total savings over the entire period, they amount to 11.2%, which equals to 26,000 kilowatt hours. And what you can see here is this the range between the building sections is from 6.8% in building C to 14.4% in building A. And between the individual months, we range from 4% here in March in building C to almost 42% for building G in April. So what we can see here that the highest relative savings in energy demand are achieved in February and April, which is actually due to the prevailing weather conditions we had there. MPC benefits from very variable weather conditions with high amplitudes in outdoor temperature, high solar radiation, or just in general very changing weather conditions. And that is what we have typically in spring, like in April here in Germany. But what we also can see is that compared to the other 2 building sections here in building section C, we have significant lower savings achieved. And this is, without going into the details now, actually due to users' influence here in the reference zones that we use to control these building sections here. The results regarding thermal comfort, we used the European norm you can see here. Basically, this norm defines different categories for thermal comfort, and the best category is the category 1 with a indoor temperature range of 21 to 23 degrees Celsius. And as we have measurement data from 2015 until basically now, we can do a nice long-term comparison of the thermal comfort here. And what we can see here for the building section A is that in 2021, when the MPC controller was active, we achieved the highest share of the category 1, so the best comfort category that was ever measured in the last 7 years of operation. The same is true for the building section G here. Also here we had 86% of category 1 indoor thermal conditions. So building A and G, we achieved larger share of category 1. A little bit different, it looks in building C here again. Here you can see that there's no real effect on the thermal comfort with MPC. So the thermal comfort is fairly average compared to the previous years of operation here. And this is again due to occupants' behavior in these reference zones, these offices that we used in the controller model. To conclude the results, in comparison to the default RBC strategy, a monthly average savings of 5 to up to 42% were measured during the 6 months investigation period. The potential for savings is actually dependent on the prevailing weather conditions, and MPC performs best in the month between the seasons, like April here. We could see a significant improvement in thermal comfort in 2 out of 3 building sections, but we also could see is that the occupants' behavior has a strong influence on the performance of MPC here, both in regard of energy efficiency and thermal comfort. Yeah, short just outlook. What's missing, of course, we could roll out the MPC control strategy in the entire building, not only in 3 building sections, as we did so far. And we also could investigate the cooling operation mode. We didn't do that so far. And yeah, then we could do like an investigation of the MPC performance for an entire year. And yeah, that's the end of my presentation. Thank you for your attention.
Thank you. We have time for questions.
Thank you. Looks like nice work. I was wondering about the energy savings. You show percentage, but I was wondering what is it exactly that you measured? Is it the thermal energy of the concrete core activation circuits, or at the heat pump, or?
No, that's the energy demand only of these thermoactive ceilings.
So chances are that part of the load is being taken over by a air handling unit.
Yeah.
Yeah. Okay. And then in this slide, I think you mentioned it shortly, but it's remarkable that there's so much difference in savings between months and buildings, because at the end of the day, it's the same location, the same weather.
Yeah.
It's the same reference control. And you've got a data set with, again, the same control in it.
Yeah.
So it's really remarkable that you've got these big differences between
the buildings.
And also it's the same MPC essentially, but okay. Yeah. So yeah, there's something going on there. It's really not that. Yeah, it raises questions.
Yeah, as I said here, like in building C, we had problems with the users. Actually, we had there were users who like opened the window for an entire weekend in winter. So we had a real temperature drop there, and yeah, I think it's
once a user can open windows, they say no more.
Yeah. So you can imagine that's very difficult for the controller here then.
Great, thank you. Other questions? Yeah.
Thank you for the presentation. There's a question in the chat box. What do you think is the degree to which thermal coupling between controlled and uncontrolled zones affects your savings, especially in building A?
That's a good question. That's because I've heard your presentation, and you stated that these coupling effects have a significant impact here. But it's hard. I don't really can tell if there's or to what amount the effect is here, because obviously the building A and C, they are kind of coupled with building B in between, which is RBC controlled. But yeah, I cannot really tell to which amount this affects here the energy savings or the thermal comfort. But there is an effect. I think so too. Yeah.
Maybe one more quick question. Anybody? Okay. Thank you.
Okay.